सर थोड़ा सा इशू है कि वो माइक्रोफोन हम यूज कर रहे थे
वो नहीं है,
वो सही दिनी के पास
अभी वो यूज कर रहे हैं या फिर?
अब मुझे नहीं पता, मुझे सेटअप के लिए बोला था वहाँ पे, वो उन्होंने अपने पास ही रखा था
तो उसको कुछ और नहीं
सेशन
है?
का। उसके लिए कन्वर्जन में हमने किया कि उनकी ऑडियो जो है
ओके, ठीक।
स्टूडेंट की वो माइक से चली जाएगी। हेलो हेलो हेलो।
Interview benchmarking?
Yes.
Okay, great. I'm just going to pull up chat over here as well so that I can see. Okay, there we go. Okay, cool. Well, it's good to be back. This is the third and last part of our lecture series, and today we're going to be discussing quantum supremacy, in particular the recent quantum supremacy experiment by Google that made headlines across the world. And what we mean by quantum supremacy in particular is solving some problem much faster than a classical computer. So in particular, it's going to be, what we have in mind is basically some problem that's exponentially easier for a quantum device to solve than it is for a classical computer. And the idea is that if we have this kind of exponential separation, then you could, in some sense, think that, even though these are, of course, computable things, so in principle, a classical computer could compute this problem. Practically speaking, it's essentially infeasible for a classical computer to solve it, whereas for a quantum computer, you could actually use it in a reasonable amount of time. For a classical device, it could take 10,000 years, but for a quantum computer, it could take a few minutes. That's essentially the idea. I noticed that I'm saying solve some problem, not necessarily some useful problem. So a lot of people, this is a common critique of the quantum supremacy experiment, that it's really just as a kind of demonstrational thing, right? It's not really geared towards solving some practical problem of interest, like combinatorial optimization or something like that, right? Which could have immediate practical benefits across businesses or across even of scientific value or something like that. This arguably has scientific value in the sense that it's maybe the first time that someone has been able to show that a quantum computer could do something exponentially faster than a classical computer can. But you should really think of this as kind of a stepping stone towards bigger and better things. So the experiment that Google performed to demonstrate quantum supremacy is based on this idea of the cross-entropy benchmark. And the key benchmark idea is that essentially there is good theoretical evidence to believe that bit string outputs generated from random quantum circuits, which we'll define presently, are exponentially difficult for classical computers to reproduce. So those of you who have a taste for kind of the more theoretical side of computer science, I've posted some references over here, and they basically, I won't go into too much detail about these, but essentially what they say is that we'll say exactly what we mean by bit string outputs generated by random quantum circuits, but the idea is essentially, again, remember that quantum computers are essentially devices that prepare probability distributions over bit strings, right? And so the idea is that these quantum computers can prepare certain probability distributions that take a very long time, that are exponentially costlier for classical computers to produce than they are for quantum computers. So if we can produce such a bit string and show that we are actually sampling from such a probability distribution, then that's basically a demonstration that that your quantum computer is doing something that a classical computer cannot do. And so one has to sort of show mathematically that no classical computer, in fact, could be able, is able to do something like that. And these papers kind of go into the mathematical side of that, which is, in computer science, I guess this theoretical side goes by the name of complexity theory. So okay, So the very first thing that we need to do is we need to understand what we mean by random unitaries. So, on the previous slide, I used the word random quantum circuits, but remember that when we write quantum circuits, the programs that we've been writing or the gates that we've been using to act on qubits, all of them are unitary operations, right? So what we really look to understand or seek to reproduce are these random unitaries, right? So, and what we mean by a random unitary in technical terms is something that's drawn from the so-called Haar measure. Now that might be a scary sounding name. Again, I've put a few references over here. In particular, this third reference, Sampling Random Quantum Circuits, A Pedestrian's Guide, I think is a wonderful read for those of you who kind of want to understand XCB from the ground up. There's a lot of literature around this. There's very few kind of review articles, and this one I thought was a nice review article. But there's other stuff that goes into specifically how you draw matrices from the so-called Haar measure. And what it really means is essentially that you're if you have some space, right? What does it mean to say that you pick an element from this space at random, right? So if you have, like, say, if you have a dice, for example, right, the object that we discussed plenty last time, and you say, like, okay, I want to pick a value on the dice at random, then if it's a fair dice, you would say, okay, with 1/6 probability, you would pick any of the numbers 1 through 6, right? That's a useful notion of what it means to draw some random face of the dice at random. Likewise, if you have, say, some continuous, say, like if you have like a uniform distribution over, say, like a flat space, right? Like, I mean, you were supposed to generate some a number between 0 and 1, for example, right? You could imagine that you could essentially draw any number between 0 and 1 with equal probability, right? More specifically, I suppose when we're talking about probabilities over uniform or continuous things, we have to talk about the probability of going from specific intervals. But you could say that, like, okay, if I, on the line between 0 and 1, it's equally likely that I draw a number between 0 and 0.1 as it is that I draw from 0.1 to 0.2. Now that's for flat spaces, right? And the analogy extends straightforwardly to not just lines, but also rectangles and also cubes and so forth. But if you have curved spaces, like you have on the sphere, for example, then things get a little tricky, right? Like, you can't just say that, like, that analogy of, like, okay, it doesn't matter whether I draw from 0 to 0.1 or 0.2 to 0.3, as long as my interval is the same size, I should get the same number of points if I draw things at random. Over here, that's not the case, right? Like, so imagine, like, we want to pick some random point on the surface of the Earth. Now, the surface of the Earth is completely specified by two numbers, the longitude and the latitude, right? So you could imagine, you could say, like, okay, let me pick, some value of the longitude at random. And when I say at random, I'm saying, like, if I pick it uniformly at random, right? So, like, I mean, if the latitude, I guess the latitude runs along the equator. So the latitude, if I pick some number between 0 and 2 pi, right? And if I say my longitude, which is some number between 0 and pi, if I pick that uniformly at random, then I'm not going to actually be picking a point on the surface of the Earth at random. In fact, I'm going to, things are going to be much more densely packed in some places than in other points. So if I really want to pick points on the sphere at random or uniformly at random, I have to account for the fact that there's basically, the equator in some sense is larger, right? Like, I mean, the circles that wind around the surface of the Earth are larger at the center than they are towards the North Pole, right? And so, like, a unit area covered by, say, like a small latitude, and let me get my pointer over here. So if I have, like, say, a small kind of, longitudinal interval over here, that captures a much smaller area than if I have the same longitudinal interval over here. That captures a much, much bigger area. So I have to account for that. And so the way that I draw will, like, I mean, the probability distribution that I have to draw from for my theta and phi is a bit more complicated than just the uniform distribution. That's really what the Haar measure ultimately sort of accounts for. And the space of matrices, the space of unitary matrices over n qubits, which we, which we've discussed before, it's the basically unitary matrices, and you can ignore an overall phase. So this is the special unitary matrices over the, of dimension 2 to the n. And so these things, essentially, this is also some kind of a curved space. And so in order to draw elements of this space at random, uniformly at random, you need to draw from the so-called Haar measure. Okay, so, and of course, like there's all these references that go a little bit deeper onto what the Haar measure is and how to actually do it. I'll provide you guys with a function so you don't have to, and and also reference for why that function actually does reproduce the Haar measure and so forth. But you don't have to worry about like how to actually implement this for yourself, and just take it as a given. The important thing for random quantum circuits at the cross-entropy benchmark, the essential concept over here is this thing known as the Porter-Thomas distribution. So the Porter-Thomas distribution, as the name implies, I mean, it's named after these two dudes, Porter and Thomas, but it's a probability distribution, right? It's so let me just, instead of saying all sorts of things that one could say about this distribution, let me just tell you how one could generate this, right? So the idea is, here's the following recipe. First of all, you fix some random bit string, okay? And I use the word random because I'm actually saying like it doesn't have to be uniformly at random. It could be literally any bit string. Pick your favorite bit string, okay? All zeros bit string or 0011001, whatever, right? But fix that once and for all, right? And now do the following. So for several trials, draw a Haar random unitary. And again, right, like we talked about how drawing a random unitary is kind of an involved process, right? Like, I mean, it's this curved space, and so one has to draw from the Haar measure and so forth. So there's a specialized way in which one has to draw from, this space of unitary matrices. But, there's some function that is able to do this, and so call this function and draw a random unitary. And now calculate and collect the probability that once this unitary applies on the all zeros starting state, right? So imagine, like, I mean, this unitary U is really a proxy for some random quantum circuit, right? Because quantum circuits are, at least in the ideal case, in the noiseless case, they're basically just unitary operations, right? So this unitary operation, it applies to the starting state, which is the all zero state. That's what this thing over here does, right? And so now it's produced some final quantum state. And now what we're saying is like, okay, in this final quantum state, what is the probability of sampling the bit string that we had fixed in advance, right? And so I compute this amplitude, and then of course I take the absolute value squared, and that's the Born probability of sampling the bit string that I had fixed in advance in this quantum circuit or quantum program that I have specified by the unitary U, where U in turn is some unitary or a circuit that I have drawn from the Haar random measure, okay? So if I repeat this for several trials, and I, each time I do this, I collect the probability, then now if I plot the distribution of these probabilities, right? So remember now that I'm talking about the distribution of probabilities, right? So this is, it can be a little hard to wrap one's head around this, but this is really like a meta probability distribution, right? So normally when we talk about the distribution of something, that means basically what's the probability, that's like a probability distribution over some configuration space or something, right? For example, like the probability distribution over fair dice is like the uniform distribution over 6 numbers, etc., right? Now we're talking about the probability distribution over sampling probabilities. Okay, and those sampling probabilities are the probabilities of sampling some bit string that I had fixed in advance. And so if you compute that, essentially you'll be able, that meta probability distribution goes by the name of Porto-Thomas distribution, and essentially it looks like this, where d is a normalizing constant, and it's essentially an exponential distribution. Okay. Um, Pictorially, it looks something like this, right? So probabilities being some numbers between 0 and 1. I'm basically deciding to cut this off at 1. Notice that, this number, e, so e to the minus d times p, like, I mean, this really is defined over all, like, I mean, you could basically take any value of p over here, and that would still be fine, right? But then it won't really count as a probability distribution. So technically speaking, like, you should cut this, this p should really only be defined between 0 and 1, and then, you should like normalize that by a total integral of this whole thing between 0 and 1. But if you actually carry that exercise out, you'll find that it basically looks almost the same as this thing. So good. Okay, so this is basically how you would generate something like the Porto-Thomas distribution, and here is the ideal Porto-Thomas distribution. This is the empirical distribution. If you run this, say over I don't know, like a few hundred trials or something. And this vertical line over here represents the uniform distribution. And by the way, this is all also described in a bit more detail in this blog post that you can check out that I wrote with Will Zhang from Goldman Sachs. Check it out. There's it does go into like how you could generate a graph like this, and this is actually one of the exercises that I would suggest to you all to do for yourself as well, and then build on something similar. But okay, let's try and unpack this graph over here a little bit more. So a few things to notice. This dotted vertical line, this represents essentially the uniform distribution over all over all bit strings, essentially, right? So if I have, let's go back to the idea of this Porto-Thomas distribution being a meta probability, right? So if instead of drawing a hard random unitary, suppose I always just drew Hadamard gates, for example, right? If I always drew Hadamard gates and acted Hadamard gates on all my qubits, so that's like the quantum dice experiment, right? And so what I'm doing there is, no matter what bit string I choose, it's always going to have a sampling probability of 1 over 2 to the n, right? 1 over the dimension, or the number of bit strings. And so, if I repeat this several times, no matter how many number of times I do this, if I always just get the number 1 over 2 to the n, then if I plot the distribution of 1,000 list number, each number being 1 over 2 to the n, then it's basically just going to look like a delta function spike that's centered at 1 over 2 to the n, right? So the Hadamard gate is really what I mean. It's kind of like a that's really what I mean by when we say, like, if we're just uniformly sampling across all bit strings, right? So the uniform probability over all bit strings is a fairly trivial probability distribution to produce, right? I don't really need a quantum computer to produce a uniform probability distribution over bit strings. I can do that quite trivially with a classical device. In order to generate bit strings from a much more interesting, more complicated distribution, for that I might need a quantum computer, and something like this, for example, it's not necessarily easy for a classical computer to reproduce. So that's essentially the idea. And notice also that this is like basically like the average of this of the probabilities that you see plotted over here. So what that means is that while on average, if you fix some bit string and you say, like, okay, like, having fixed this bit string, let me now sample different quantum circuits, and each time I run a circuit, I'm going to compute what the sampling probability of this bit string is, right? And those sampling probabilities is what I'm going to compute the distribution of. Then I'll find that on average, it's about 1 over 2 to the n. But sometimes it can be larger than that, and sometimes it can be lesser than that, right? And so notice that, it says nothing about which bit string we're talking about. It's completely agnostic about that, right? It could have been the all zeros bit string, or it could have been some other bit string that you're talking about. As long as you fix that bit string from the outset, then you sample random quantum circuits, okay? Um, so that's the Porter-Thomas distribution. It's a distribution that you can generate using, and again, I mean, let me be very precise and let me be clear about this. We're not saying that we cannot generate the Porter-Thomas distribution classically, right? In the sense that like I can basically just describe a sampling probability at, numpy dot exponential minus d times a number between 0 and 1. That's a probability distribution I can define very quickly on a classical computer, right? What I'm saying over here is that, uh, I can produce these probability distributions over bit strings such that if I collect the sampling probabilities of some initially fixed random bit string, then those meta probability distribution, that behaves in this particular form. That's the main statement that is basically easy for quantum computers, but believed to be uh, difficult or basically infeasible for classical computers. Okay. Now, that was the Porter-Thomas distribution. However, for the XCB, or so, when I say XCB, cross-entropy benchmarking is oftentimes just abbreviated to be XEB. So you might hear me saying XCB more often than cross-entropy benchmarking. But for XCB, the more relevant distribution, as it turns out, is not exactly the Porter-Thomas distribution, but something that's closely related. And again, because it's a distribution, I'll give you what the mathematical form is. It basically looks like that. And I'll tell you how to actually numerically sort of recreate it for yourself. And the way to do it is you say that for several trials, you will draw a hard random unitary. Next, you will sample a bit string from the produced circuit, okay? So what I'm saying over here is that at U on the initial starting state 0, okay? And now you produce some quantum state, right, from which you can sample bit strings. Sample a bit string. Sample a bit string X, it's going to be more likelier than not, it's going to be one of the bit strings that has a high probability according to this random unitary U, right? So that's basically the idea that U gives more on, U, if it's some random circuit, it's going to give, say, it might give more preference to this particular bit string than another. And so there's a high probability of sampling some bit strings over others. Okay, so you apply U, you sample a bit string X from the produced circuit, and so now that you've sampled it, collect the ideal probability of having sampled that particular bit string from that particular circuit or from that particular random unitary U. Okay, so this can be a little subtle. So let's make sure we all understand this, right? Previously what I was saying is that X was fixed in advance, right? Over here, I had fixed the bit string in advance, and then I was basically sampling random unitaries, and then I was collecting the ideal sampling probabilities of that bit string that I chose. Here, what I'm doing is that I'm drawing a random unitary, just as before, but now what I'm doing is I'm sampling the bit string from the random unitary itself, okay, or more specifically, from the random unitary being applied on the all zero state. And so now that I've found what this bit string is, I can now calculate and collect the ideal sampling probability of this particular bit string, okay? And so now these are, again, just numbers, right? And I'll collect them in a list, and I'll plot a histogram, and the distribution of those probabilities should look, coming out something like this. And it looks a little bit more different than the Porter-Thomas distribution. But it's, again, kind of like the one that's the more relevant distribution for XCB. So here's how the specific or the actual XCB score, is actually calculated. So Historically, there was another version of this score, but in the supremacy experiment that Google reported, and you can, by the way, read you know their Nature paper, or sorry, this is the supplementary information. This is the Nature paper. This is like the main article in which they describe their supremacy experiment, and this is kind of a longer read that goes into supplementary information. So I would encourage you all to go through these for yourself as well. But essentially, if in that latest formulation, what they consider is the so-called linear XCP metric. And the idea is as follows. So we're going to consider some black box, right? And this black box is going to be either a classical or a quantum device. And we're going to say like, okay, like we have some prescription of U, which is ideally a hard random unitary, but in practice, it's going to be some random quantum circuit. And we'll talk a little bit about like why it's okay to talk about random quantum circuits instead of hard random unitaries. But essentially, you take a quantum program as input, and this black box is going to tell you, it's going to basically sample a bit string according to the input U. It outputs a bit string, okay? So like, I mean, you feed into the black box gives you some bit string. Now your task is to compute the ideal sampling probability of that bit string according to the quantum circuit specified by this unitary. Okay, so that's basically like you acting on zero, giving its sampling probability. Give me just one. Sorry about that. Okay, so essentially we have U as a prescription, of the random quantum circuit. We feed it into some black box, which again is some classical or quantum device. This black box spits out some bit string sample, and our task is to essentially compute what the ideal sampling probability is of the bit string that we received. Okay, and so that is something that we would collect together. Like this is the ideal probability. We will collect this in a very long list, and then we will take the average of that very long list. That's what these brackets indicates. And now that we've computed what this average is, we will simply multiply it by the dimensionality of the Hilbert space we are working in, which is basically 2 to the n, and subtract the 1. And there's some nice properties about this particular metric, which is that for if it's a purely classical computer, then this should come out to be on average, and this is where like the complexity theory and everything comes into play. But basically the idea is that if you have a classical computer being your black box, right? And you say you give it some prescription of your random quantum circuit. So this could be like a Python program that you wrote, right? Like, I mean, it has a bunch of instructions like carry out a Hadamard on this qubit and then a C0 between these two qubits, and then a Hadamard on this other one, or RY rotation on this other one, and then a C0 between this pair, et cetera, et cetera, et cetera, right? Like it's some long string of instructions. That's your input to this classical computer. So the idea is that if this classical computer gives you a bit string in polynomial time, right? So in complexity theory, there's a difference between, like if something performs a computation in polynomial time, which means, in time that scales as n to the some power, like n squared or n cubed or something, where n is the size of the input. In this case, like, if it scales, if it gives you a bit string in time that is proportional to some power of the number of qubits, right? And not exponential in the number of qubits, not something that scales as 2 to the number of qubits, but something as number of qubits raised to the power 2 or 3 or something like that. Then, there's kind of mathematical arguments that argue that essentially this average is going to be essentially just 1 over the dimension. It's just basically going to be on average the uniform distribution over all bit strings. Okay, and so that's why like the essential property, the essential thing that you're actually computing on these devices is of course these ideal probabilities and their averages, but like we're just choosing like this particular form of the equation so that this number comes out to be 0 for classical computers. And in the case of quantum computers, you can show that in the ideal Porto-Thomas regime, for a large enough number of qubits, this thing actually approaches the value 2 over d. And so this becomes in that limit equal to 1, right? So if it's an ideal quantum device, then it's going to spit out this number equaling 1. And if it's a quantum device that's basically operating not any better than a classical device, it's going to be 0, okay? For purely classical computers, it's always going to be 0, right? But if your quantum computer is doing something quantum, right, then it's in general going to be some number between 0 and 1. So you can essentially, in some ways, declare, arguably, you could declare supremacy if you can show that the number that you produced on your quantum computer is strictly speaking greater than 0, which is what Google did, essentially. One point I will mention is that even though this black box is something that could be it's a classical computer, or in general for our experiment, or in the context of the quantum supremacy experiment, it's like a noisy quantum computer, right? And so a noisy quantum computer produces some bit string that's like maybe less than ideal. But this ideal probability, this is something that you still need to compute using an ideal simulator, okay? So this is why actually, like, I mean, you like the ideal regime of showing quantum supremacy is something like of the order of 50 qubits, because it's about 50 qubits where you can still sort of reasonably simulate quantum computers classically, but beyond that you cannot really simulate. And it's a little tricky, like, so you might ask, okay, well, if we have to simulate the entire thing, then how is there a quantum advantage of any sort? Well, the idea is that like the simulation takes a lot of time, right? Like it takes a lot of supercomputing time for one thing. And in the case of like the so-called supremacy circuits that Google, like, I mean, that Google also ran, that like they had some argument to show that the XEB as calculated over here, it still comes out to be some number greater than 0, but they can only approximate it. And if they wanted to exactly calculate it, then that would take like, I think they came up with some ridiculous number, like tens of thousands of years or something like that. Whereas for a quantum computer, it only happens in a few minutes. Okay, so good. So we talked about random unitaries, but on an actual quantum computer, like we don't actually produce random unitaries. We have access to gates, right? Like we have single qubit gates and we have 2 qubit gates. So the idea is essentially that if we have gates that we can draw randomly, uniformly from some universal gate set, and remember that a universal gate set just means I can produce all single qubit gates, and I have one 2 qubit entangling gate. Then essentially I can perform universal quantum computation in the sense that I can, any unitary that you can imagine, I can express it as a product of these 1 and 2 qubit gates to some arbitrary precision, right? So if you draw uniformly randomly from some universal gate set, these converge exponentially quickly to Haar random unitaries. This is basically like the ideas described in, here's some references that go into a bit more depth into this, right? So, but the idea is essentially that instead of random unitaries that one is drawing from the Haar random measure, which is helpful, when you're playing around with these concepts, as you will as well. But on an actual quantum computer, like, you can just equally as well just draw randomly from a gate set. In the case of Google's experiment, they had these particular single qubit gates, which they call respectively the square root of x, y, and w. And these are, you could think of this as like essentially like a power 2 rotation about the x-axis, power 2 rotation about the y-axis, and power 2 rotation about the x plus y-axis, right? So these are your single qubit gates. And then for their 2 qubit gate, they have this parametric gate over here. Notice the nice thing about this is that, so the computational basis, this is like how it acts on the 0, 0 state, right? It just produces the 0, 0 state again. On the 1, 1 state, it just applies some overall phase. And on the 0, 1 phase, sorry, on the 0, 1, it actually mixes the 0, 1 state with the 1, 0 state, okay? And likewise with the 1, 0 state, it mixes up the 1, 0 state with the 0, 1 state. So essentially, did I lose my wire? Okay, there we go. Yeah, so this column describes how it acts on the 0, 1 state. This column describes how it acts on the 1, 0 state, and this column describes how it acts on the 1, 1 state. And so the point is that, like, 1, 0 gets, gets sent to a superposition of 1, 0 and 0, 1. Sorry, this column acts on the 0, 1. And likewise with 1, 0, right? 1, 0 gets sent to a superposition of 0, 1 and 1, 0. And so what that means is that the total number of ones is preserved. Okay, so like if 0, 0 only gets sent to 0, 0, then the total number of ones is 0. 0, 1 gets sent to 0, 1 plus 1, 0. Total number of ones is 1. Same with 1, 0, and then with 1, 1, it just gets sent to itself. So the total number, of ones is 2. And so that Hemingway preservation is actually something that's very useful for doing quantum chemistry experiments in particular, which is something that the Google group seems to quite like. And there the idea is like, this is maybe straying a little bit, but I just wanted to give you some perspective on why they used this particular gate. So there in quantum chemistry, like you model, you use qubits to model orbitals, and each orbital is either occupied by an electron or it isn't. And the total number of electrons in your molecule has to remain conserved because of particle number conservation. So the number of ones that you have in your qubit register as you simulate the qubit, as you simulate your system, the number of ones has to remain preserved. So that's why this particular 2-qubit gate is nice, okay? And it also has some other nice properties. It makes classical simulation difficult in the case of XCB. It has, it even has some uses in the QAOA algorithm. So for those of you who ventured into reading about the XY mixers for, like say the coloring problems, graph coloring problems, and so forth, you'll realize that, like this is basically like an XY gate. The XY gate is maybe like a subset of this. So, it has plenty of other uses in applications as well. So it's a nice gate to have. On Rigetti, however, like, so there's one way to simulate something like this on, so you could like basically take exactly these 1-qubit gates and this 2-qubit gate. Of course, like these are not native gates on our stack, but in Pikewill, it doesn't really matter, right? Like, you could like just define, well, I guess we could, sorry, I take that back. We can do basically any single qubit gates, but at the Quill level, we only allow Rx pi over 2 and Rx minus pi over 2 and any RZ rotations, okay? So Ry pi over 2 is going to get compiled into something that's, in terms of RZs and Rx pi over 2s. Likewise with Rx plus Y pi over 2. And this again is something that's not exactly defined at the Quill level, but you can compile it down to something that is defined at the Quill level. So for example, here the W square root gets decomposed into a product of 3 fundamental or basic defined native gates in Quill. And here I'm basically defining an FSIM gate for some values of theta and phi. I think theta is like pi over 2 and phi is some value. And notice that it's a very long chain of like single qubit gates and at least, I guess, two 2-qubit gates. We have an XY gate. XY is a parametric gate, which we haven't really discussed, but it sort of looks like this previous gate that I showed you. But the important point to note is that this is a 2-qubit gate, and CZ is another 2-qubit gate. Okay, so it gets compiled to 2-qubit gates and a whole bunch of 1-qubit gates. So even though Google used this, we're not going to use this gate set. Okay, we're going to use something that's more native on our stack. And here's one, for example, gate set that we could use. Like, for single qubit gates, we could use Rx pi over 2, we could use RZ pi over 2, and then we could use an RZ pi over 3. And for our entanglement gate, we can use the CZ gate. One of the advantages of our single qubit, so of course the advantage immediately is that, like, I mean, these are something that if you look at Quill or native Quill, these are all gates that are defined in native Quill. Okay, so as I mentioned, like CZ is a 2-qubit gate defined in native Quill. RX pi over 2 is a gate that's defined in native Quill, and any value of RZ does the job as well. RZ pi over 2 is just like nice in analogy with RX pi over 2, and then RZ pi over 3 is just something that we need to add to this set of other gates, because if we only had these gates, RX pi over 2, RZ pi over 2, and CZ, then this is, these are so-called Clifford element gates. And there's a theorem that says that if you have only Clifford gates in your quantum circuit, then that's something that's actually quite easily classically simulable. We won't stray into that, but those of you who are curious, like look for, like if you just Google Clifford simulation, you'll read about things like Pauli stabilization group and stuff like that. And it has to do with, it might be a nice segue for you guys to into quantum error correction and so forth as well. But, you can just take it on faith right now that, like, I mean, if you just had Clifford element gates, then that's actually quite easily classically simulable. So we have to add something else to our gate set. And that something else, in this case, you could think of RZ pi over 3 as a non-Clifford element. Another nice thing about this gate set is that RZs actually on superconducting qubits, they're not exactly pulses. Okay, so the RX pi over 2 and the CZ, these are actual physical pulses that we have to apply to qubits. Okay, and like, I mean, these actually perform some kind of a physical operation on qubits that we, that's like physically actually there. Whereas with the RZ gates, like, I mean, this is actually, we call them virtual gates because this is something that, like, we can sort of enact using just tricks in the control system hardware. Okay, not on the physical qubits themselves, but just like on the control rack. Like, I mean, we will just like sort of perform some sort of bookkeeping tricks and say, like, okay, if you're applying an RZ on this qubit, then, like, okay, on any future gates that we perform in this qubit, I better, I'm just going to make a note that, like, the user wanted an RZ gate on this qubit. And so now I'm just going to make a note of that. And the next time the user applies, say, an RX or a CZ involving this qubit, then I'm going to do something slightly different than what I do normally. But the idea is that, like, these basically come cheap. Okay, so that's another sort of advantage of using a gate set like this. But then, now you're back to doing the same thing. You would basically say, like, okay, I'm going to pick, so I'm going to have, like, repeating layers of gates. Like, in the first layer, I'm going to pick some gate at random from this list and apply it to, qubit A. Pick some gate at random from this list, apply it to qubit B, et cetera, et cetera, et cetera. And then in the second layer, I'm going to just have, like, some 2-qubit, entangling layer. So, like, I'm going to have, like, CZs on these 2 pairs of qubits, CZ on another, CZ on another, et cetera, like that, right? So if you do it like that, and you again compute what the ideal probabilities are, you will again be able to recover something like the wave function simulator. And this is one of the exercises that you all should do as well. But this I think is a good sort of like just like, I mean, we should pause here and check to see if there are any questions, because if there's any confusion about what this graph is, which is the graph of the Puerto-Thomas distribution, we should definitely stop and make sure that those get clarified, because this is really like the heart of the matter of the quantum supremacy experiment. So are there any questions so far?
Questions? Online? Doesn't seem like there is any.
Okay. We will press on in that case. So, okay, so I was talking about, using the wave function simulator to simulate what the exact or to compute what the ideal probabilities are. But that's not how, that's not a very scalable process, right? So what Google's team and company did was they used the classical simulation technique of this of tensor network contraction. Okay, um, so we'll talk a little bit about what this means as well. So tensor network contraction involves. So we're just going to unpack all these words, right? So first of all, what is a tensor? By a tensor, we simply mean some multi-indexed array with k indices, and the k indices are its rank, right? And each of them can run over at most m different values, and the number of those different values is called the dimension. Okay, so for example, in NumPy you could do something like this, right? So like you pick you pick 16 different numbers uniformly at random between 0 and 1, and now you reshape them into this 4 indexed array where each index runs over 2 values, right? So this is 2 to the 4, which is equal to 16. And so this is a rank 4 tensor, right? So this is this has 4 indices, right? And each of those, and there's a rank 4 tensor of dimension 2, because each of the indices runs over 2 possible values. If there's any kind of like physics or math students in the room, by the way, this is a somewhat different definition of tensors than the definition of tensors in something like physics, where they have more structure, right? Like they're sort of like considered generalizations of vectors, and vectors in turn are supposed to have like certain nice transformation properties and so forth. But in computer science, by and large, or at least in computer programming land, when people talk about tensors, they really are just talking about multi-indexed arrays, really, and nothing else. So it's the same tensor as in TensorFlow, for example, if for those of you who might have played around with that. And so pictorially, they often look something like this, where you have a box and they have some legs. And this is, for example, a rank 5 tensor. This is how you would represent something like that. Written, out in I guess like in alphabetical form, it would just be like IJKLM, right? And those 5 indices would be like the 5, the 5 ranks of I guess that particular tensor. So that's what a tensor is. A tensor network is simply a network of tensors, right? So like you could pictorially, like the best way to imagine it pictorially is like if you have like this rank 5 tensor, and one of those indices you could imagine is being shared by some other tensor which is rank 1. This index is being shared by this other tensor rank 1. This is a rank 4 tensor which shares 2 of its indices with this one, and this one with that one. So this is like a network of tensors. And notice that this is like an undirected graph, right? Because there's no special direction to these edges. I'm not saying that this edge is an arrow pointed from here to there or from there to here. It's just like it's just an edge between them. So it's undirected, and it has a max degree of 5, which means that if you consider any of the vertices in this graph, the maximum number of edges that any one node or vertex has is 5, which essentially belongs to this particular thing, this central node in this example. So that's a tensor network. Finally, what is a tensor contraction? So tensor contraction between 2 tensors is given as follows, right? So like we'll say that if A and B have, say, P edges that are shared between them, right? We can contract these edges, and we can contract them and say, so A and B share P edges between them, but A has N other edges, and B has M other edges. Then basically we can contract these inner edges, the P of the edges that A and B have in common, and produce a new tensor, C, which is going to have N plus M legs, or N plus M indices. So in equation, you could think of it like this. Essentially what the contraction is, it's a summing up over those internal indices, right? So what it's saying is that this new tensor C, which is an N plus M rank tensor, is going to be described as follows. So you take the tensor A, And the tensor A, like for some specific values of each of these n plus p indices, it's just some number, right? And so B, likewise, for each values of these indices, J1 through JP, K1 through KM, that's again just some number. So add up, multiply those numbers while summing up over all these indices or over all these edges, 1 through P, where J1 is basically like the values that this edge can take. Remember, that's the dimension, right? Like the number of values that each edge can go over. And so you're just like summing over all those edges essentially. And that's what essentially what the contraction refers to. Okay, so now you're getting rid, you're summing over these inner P edges, and you'll get rid of these edges, and what you'll be left with is n plus m edges. And this entire operation is exponential in the total number of edges involved. So like, I mean, P edges which are being contracted over, but also n plus m other edges that belong to A and B collectively. So it's exponential in the number of those, the total number of those edges involving these two nodes. So as an example, like, I mean, imagine if A was some rank 5 tensor, right? So it has like 3 edges that have nothing to do with A, or 3 indices that have nothing to do with, with B. And 2 of them, like it shares those edges or those indices with B, and B likewise, or similarly, is some rank 3 tensor, and it shares 2 of its indices with A, and one of those edges has nothing to do with A. Now, if you sum those, essentially, like the IJM, like, I mean, those indices, like, I mean, they carry over to this new tensor C, and its fourth index n comes from B, but the 2 inner ones, those are just contracted over, okay? And so C, the new tensor is some rank 4 tensor, again, of dimension 2, right? And as a very explicit example of the following, so if we break apart, like if we give an even more specific example to this particular thing, so over here, for example, like, I mean, C, if essentially what I'm saying is that IJMN, if it's dimension 2, that like, you could say that like, okay, I runs over the values 0 and 1. Likewise, J runs over the values 0 and 1, and M runs over the values 0 and 1, and N runs over the values 0 and 1. So in all, I have to compute 2 to the 4 numbers, starting with like the all zeros bit string, and then going to 0001, 0010, etc., until I have like all 2 to the 4 of them. And the way that I would compute each one of these in turn is I would basically sum over the possible values of K and L in this expression, right? So here I have A000, KL, BKL 0, and then K and L each can take on values 0 and 1, because this is a, these are both dimension 2 tensors. So in the first case, I have them equaling 0, 0, then I have 0, 1. Notice it's again 0, 1 over here. Then it's 1, 0, 0, 1, 1, 1, right? So these, there's going to be 2 to the number of indices that are being contracted over here, right? Because 2 is the dimension. And the number of indices that are being contracted, that's, like that's how many times I have to multiply 2 to get the number of products in this sum, right? That's the number of computations that I have to do. So in all, I have like 2 to the 4 numbers to compute, and each number takes 2 raised to the power 2 terms, right? That's a total of 2 to the 6, which basically you can check that that's exactly the number of edges being contracted over, plus the number of edge that B has left over, so that's just n, plus the number of edges that A has left over, which is IJ. So, so that's basically why it's exponential in the number of, you could think of it like, as the number of the resultant, the resultant tensor plus the number of indices that are being contracted. Okay. So finally, what is a tensor network contraction? It's essentially the contraction of the entire tensor network into a single number. Okay, so what that means is that if I look at this tensor network, right, so you could think of like, I mean, for example, I can contract this particular node into this particular node, and then I've gotten rid of this particular edge, right? And this node now in some way, this no longer exists, or rather, it only had one edge, and that edge was connected to this one, and so it has no outgoing edge anymore at all, right? And so a tensor that has exactly 0 indices is just a number, okay? That's another way to think about it. And so I can basically go about, performing contractions between individual nodes of this graph. And, eventually when I contract over the entire thing, I'll just be left with one single node, and that single node has no outgoing indices or edges. And so therefore that's just a number. It could be a complex number, but it's just a number, right? And notice that the contraction ordering matters, right? So even though this is just some undirected graph, like I can be really silly about the order in which I contract my indices, or sorry, my vertices. So for example, I could, for example, contract this particular node with this particular node first, right? But that's a terrible way of contracting this network, because what that means is that now I'm going to have 1, 2, 3, 4, 5, 6 edges, right? And as we just saw, the computation time scales exponentially in the number of edges that any resultant tensor is going to have, right? And so, why would I want to do something like 2 to the 6 when I can get away with something like 2 to the 5, right? So I could, for example, like contract this first, and now I have like a rank 4 tensor, and then I could contract this with that. Now I have only 3 edges over here, and then I could contract this with that, and then I could contract this with that, right? And then I could contract this with that, and I never exceed any computation. None of my computations then ever exceed something that scales as something that is roughly 2 to the 5, right? So that's why contraction, the order in which you contract the various nodes in your undirected graph, that matters quite a lot. And it's in general, it's a hard problem to determine the ideal contraction ordering for some arbitrary undirected graph. But a lot of the research that happens around, classical simulation of quantum circuits is actually around like what the ideal, maybe there's like good heuristics and so forth for contracting quantum circuits that we can build out of, or tensor networks that we can build out of quantum circuits. And we'll talk about like how we can actually build tensor networks specifically out of quantum circuits in just a bit. So the idea is that, let's recall a few basic factoids about qubits and quantum computers. So in vector form, a qubit is given as some superposition of 0 and 1. In operator form, remember we talked about the density operator, right? The density operator is given as the outer product of the ket and the bra and its corresponding bra. So this is like, alpha 0, alpha 1, and then alpha 0 bar, alpha 1 bar. And this is like a matrix, right? And so because it's a matrix, that's why we call it an operator instead of a vector, right? Even though it's a description of the qubit state, it's not a gate or anything, right? So when we've written it in terms of a density operator, likewise, okay, well, completing this particular formalism first, like, so we can express qubit states as density operators, but we would like to express them, the density operators now in vector form, in tensorial form. So essentially the idea is that, this density operator, it has 4 elements, right? So this is like the row 0, column 0 element. This is the row 0, column 1 element. This is the row 1, column 0 element. This is the row 1, column 1 element, right? And so those 4 entries I can essentially arrange in a vector form. And I can equivalently express the same thing in tensor form as follows. So I can say like, okay, in some basis, remember a vector is just like a series of numbers in some particular basis, right? Like, if I have a sphere and I describe a point on the sphere, I can express it in XYZ coordinate system, right? or I can also express it as a vector in spherical coordinates in r theta phi coordinate system, right? But the numbers are going to change depending on which basis I use. But nevertheless, like, I mean, they're just like some series of numbers, right? So here, for example, I could choose the Pauli basis, and in terms of the Pauli basis, like, I mean, the coefficients are going to be given as this particular trace of whatever like rho is, like rho dotted with the Pauli matrices. But a more convenient sort of basis to work with over here is like precisely this this basis computed out of the computational basis. So 0, 0, 0, 1, 1, 0, 1, 1, right? So these are precisely like they correspond to like the row and column entries of the density operator in the computational basis. So some important examples, for example, like the 0, 0 state, which is typically like the starting state for a single qubit, that's just given as like 1, 0, 0, 0, right? So just that first component is 0. Sorry, the first component is 1 and everything else is 0. Or say like the 1-bit stream, right? So in that case, like it's the final component that's 1 and everything else is 0. Likewise, qubit gates could also be expressed as tensors. So here we have unitary gates with n incoming qubits and m outgoing qubits. And this time we have to express it in so-called superoperator form. So what that means is that if the qubit can be expressed as a density operator, then the gate which acts on the qubit has to be an operator on that operator. So we call it a super operator, right? And so the way that it works is like you say, like, okay, it has some indices for some incoming qubits, and it has some outgoing number of qubits. And really, like, I'm describing this formalism in a much more general form so that this is how it was originally described, so that one could also apply this to noise simulation and so forth. You can get away with like not having to do any of this. Like, well, I shouldn't say any of this, but you can get away with not having to deal with density operators and instead just talking about zeros and ones, just like qubit states. If you're only talking about unitary operators, I'll just mention that in passing. But this is kind of like the much more generalized, way to do things, I suppose. So anyway, so the idea is that like, you'll basically, its components are given by taking the trace of the following things. So you'll apply the super operator U on this product of Pauli matrices, and then you'll basically take the product of whatever resultant operator you find over here with this particular product of Pauli matrices, and that basically gives you this one of these components. And the super operator, like, so if I put a hat on it, that basically means it's a super operator. And these Pauli operators, like, because these are Pauli matrices, they're considered an operator. The way that it acts, remember when we talked about, the evolution of a density operator, it was something like rho goes to like U times rho times U dagger. That's how a unitary operator acts on some density operator, right? So you should really think of this particular product of Pauli matrices as sort of like a proxy for a density operator over here, right? So I can basically compute, some simple gates, for example, like, an R-right theta gate written in the usual qubit form, in matrix form, it looks like this, right? Its action, say, on like some density operator basis state, X could be 0 and 1 and Y could be 0 and 1. It's given as follows, right? So like R-right theta acts on the left, and then R-right dagger theta acts from the right. So, for example, its action on the basis state 0, 1 is given as follows, right? So like I could act like R-right theta acting on 0, it's going to give me something like a cosine theta over 2, and then acting on 1, it's going to give me like, minus sine theta over 2. Or sorry, like R-right dagger theta acting on, like to the left on 1 is going to give me minus sine theta over 2. And so that's why I get something like this for the 0, 0 state. And then, you can sort of like work out like what the other elements are going to be. It's basically just applying like R-Y theta, this particular matrix with like, we have a 0 over here. So it's just going to be like a 1, 0, vector over here. So whatever value that comes out to be, and then you take the transpose conjugate of this matrix, and then act that on the left, from the left on the vector 1, which is like basically 0, 1, right? And so you just take those things and you'll get some matrix, and the matrix, row 0, column 0 entry you'll find is something like this. It's row 0, column 1 entry is this. It's row 1, column 0 entry is this. And it's row 1, column 1 entry is this. Okay. So that's how this particular basis state is going to evolve under the action of the RY gate. Continuing that example, essentially what we're saying is that now we set, if this is you could think of this as sort of like representing the state of the incoming qubit, right? And RY acts on the incoming qubit and produces like the outgoing qubit. So if we use this index dictionary where like 0, 0 is like the 0th basis state, 0, 1 is the first basis state, and 2 and 3 and so forth, then basically this exercise is saying like, okay, like we're computing like we're computing the components where the incoming qubit index is 1, right? Which is basically this left index. And then the 0, 1, 2, and 3 respectively compute like the 0, 0, 0, 1, 1, 0, and 1, 1 indices, which we already computed over here. Here I'm just listing them out, right? So this is basically like, single qubit gates essentially are rank 2, dimension 4 tensors, right? So rank 2 because I have like one incoming qubit and one outgoing qubit, and dimension 4 because each of those indices can run over 4 of these states. Okay, because a single qubit density operator it's a 2 by 2 matrix which has 4 elements. Okay. Likewise, I can repeat the same exercise for 2 qubit gates. So for example, a C0, I can compute on some arbitrary, 2 qubit basis element. So likewise, just as before, basically over here, I, J, K, and L are going to run through the values 0, 0, and 1, right? So I can be 0 and 1, J can be 0 and 1, likewise with K and L. And C0, basically, I can express as the following gate, right? It's basically the projector on 0 tensor product I plus the projector on 1 tensor product X, right? So this is basically saying if this control qubit is in the 0 state, then apply the identity qubit on the target. And if the control qubit is in the 1 state, then apply the X gate on the target, right? That's what the C0 gate is. And so just as before, we're going to sandwich the C0 gate from left and right. So this, C0 dagger is equal to C0 again, but this is really like C0 dagger, right? Which is again just C0, so it's the same thing. But this is like U times the density operator times U dagger. And the only difference is that like now instead of one incoming and one outgoing qubit in the case of 1 qubit gates, because it's a 2 qubit gate, we have 2 incoming qubits and 2 outgoing qubits, and so this is going to be a rank 4 tensor. But the dimension is still going to be the same, right? Because each of the indices still goes over 4 values. And the index, by the way, is given by like the collection of these 2 things, right? Like the cat and the dog, according to this particular dictionary. So, right, so it's a rank 4, dimension 4 tensor. And if you compute out, it's a little bit of an involved exercise, but you can do it for yourself, and you'll find that it basically comes out to be something that looks like this. So it's a rather sparse matrix, or a sparse tensor in some ways, such that only these values take on the value 1, and everything else is a 0 in this case. So it gets a little easier to work with. So finally, we specified how to, we talked about how to specify qubits as tensors, right? We have, for example, the 0, 0 state could be specified as a tensor like this, and 1, 1 could be specified like this. And more generally, we could express the components as trace of rho times sigma dagger, where the sigma is 1 basis element, right? But we also specified how qubit gates could be expressed in this tensor notation. For example, this was an RY gate, and more generally, single qubit gates are rank 2 dimension 4 gates, and or sorry, rank 2 dimension 4 tensors, and 2 qubit gates are rank 4 dimension 4 tensors. And finally, measurements are specified as follows. So, like, I mean, in the case of tensor contraction simulation, we don't get all the bit strings for free. What we have to do is we have to specify a particular measurement scenario, and we say like, okay, like I want the sampling probability, or I want the quantum amplitude of some particular bit string basis uh, computational basis state, right? So I have to fix a bit string, say like 010 in the case of a 3 qubit problem, and then I will finally like use that earlier mapping. I will say like 0 gets mapped to like this projector 00, 1 gets mapped to this projector 11, etc. Right? And that projector is my final state, and that's my final tensor, and essentially that's basically it, right? Like, I mean, I know how to sort of like compute, like create tensors out of everything. Like I had like the starting state, which was the entire 00 state, so it's just a collection of these tensors, right? Then I had single qubit gates, which are rank 2 tensors. Then I had 2 qubit gates, which were rank 4 tensors. And in pictorial form, it's just going to look like a bunch of nodes with some legs, right? So 2 qubit gates are going to look like nodes with 4 legs. 1 qubit gates are going to look like nodes with 2 legs, etc. Right? And these things are the measurement ones are not going to have any outgoing legs, and the starting states are not going to have any likewise any incoming legs, right? So it's just going to be some giant network of tensors essentially. Once we form the tensor network, we can, again, like we described, like we will just simply contract the entire tensor network into a single node. And that node, you'll find, if you follow the steps carefully, that it's just going to be the trace of this measurement scenario, which is either 0 or 1, times basically the quantum circuit, right, which is again some tensor network of your single and 2 qubit gates acting on the all zeros starting state. So it's just going to be like this quantum amplitude of whatever bit string you specify with this particular measurement scenario. So that's a very that seems like a very convoluted way of doing things, right? But to impress upon you the power of this framework, here's one example that I kind of cooked up, right? So imagine a C0 ladder, right? So like these are your starting states, and like this is like qubit A, qubit B, C, etc. And all of these start off from the 00 state, okay? And what I'm interested in, somewhat arbitrarily, it doesn't really matter, but I'm saying like, okay, I am interested in running like this particular circuit. So each of the box is some RY gate of about some random angle. So it's an RY, it's a rotation about the y-axis, about some random angle, basically. And this rectangle is a C0 gate that entangles this qubit with whichever the qubits are denoted. So naively, you would say like, okay, if you were to do this sort of like the using the standard wave function simulation method, then you would have to basically think of this as a very large 2 to the n by 2 to the n matrix multiplication, right? Like, and you would say like, okay, if these are n qubits, this is like a 2 to the n by 2 to the n matrix that I have to then apply to this starting 2 to the n dimensional vector, and that will give me my my final 2 to the n dimensional vector. And from there, I can extract, the amplitude. Say I can pick the very first element and say like, okay, that's the amplitude that I'm looking for. On the other hand, but if I use it, if I use this particular technique of tensor network simulation, again, only computing the amplitude of this one particular bit string, the all zeros bit string, then you can find that actually tensor network contraction does it blazingly fast compared to wave function simulation. And this is described in a tutorial or a kind of a demo notebook that I've sent along So you should all take a look at it as well. Um, and I in fact like even went up as far as like 500 qubits for the CNOT ladder, and you can see that it takes like less than a fraction of a second. Of course, like I mean, at that point, like the probabilities of like of sampling any particular bit string gets so small that like you shouldn't really trust this number anymore at all. But notice that the time takes like it's about like a hundredth of a second, which is amazing, right? Like you cannot really simulate generic circuits over 500 qubits at all. But for this particular circuit, the CNOT ladder, you can, if you're, like, I mean, again, like with the caveat being that like you're only simulating the amplitude for one particular bit string, right? Okay, so why does it happen so quickly? It's because I can imagine a contraction ordering of this. Again, I mean, there's a very silly way to contract this entire network, right? Like I can, first of all, contract everything in the middle, right? And if I've contracted everything in the middle, then I'm basically back to, a computation that's going to scale exponentially in the number of qubits. But I can also contract everything as follows. I can contract this node with this thing, and then this thing with that thing, and then I can contract the measurement qubits, or the measurement nodes rather. These are, you should stop thinking about these as qubits, etc. Now you should just think about this as some graph. Then you can contract this node with that node, and again repeat over here, right? So contract everything horizontally first, right? Except for the 2 qubit gates. So contract like this node with that node, contract this node with that node, contract this node with that node, this one with that one, etc. Right? And then you'll basically have, you'll end up with a sequence of nodes, or a network of tensors that looks like this, right? And now this is again just like a linear graph, right? And now you can just sequentially contract these nodes in turn. And so, notice that like the ordering that I just described, using that ordering, the maximum degree of any vertex during the entire contraction process, it never exceeds 4, right? And so my computation is only going to be order, it's going to be like exponential in the number of 4, like so, like 4 to the 4, 16, not a big deal, right? Like it's not going to be exponential in the number of qubits. It would have been if I had done the rather dumb contraction ordering in which I contract everything in the middle first, but that's not the optimal way to do it, right? There's other ways to do it, and so you should take advantage of that. But more generally, for example, in the case of random quantum circuits, you can show that like at least if like the qubits that you have all lie along, say, a one-dimensional lattice, right? Then this is something like the true, like the cost of the classical simulation done in this manner. It scales exponentially in the minimum of either the depth or the number of qubits, which is the width. And more generally, it scales exponentially in what's known as the tree width of the graph. And I won't really go into that, but if you should, for those of you who are more interested, you should take a look at this particular paper. This is the first paper that actually talked about simulating quantum computers using tensor networks. And these 2 other references, they are kind of like more in the context of using that technique to simulate these so-called random quantum circuits, in particular for the quantum supremacy experiment that Putin did. So I'll stop there, and I will also, since we are on the topic, I will share, I will go over the notebook that I had prepared for the tensor contraction simulation. And then, because today is the last day, I wanted to like leave some time to discuss, previous material. And there was also another exercise that that you did not see the last time. This was for the gate error mitigation that I'd like to go over today as well. And then we can take any, whatever questions you guys might have. But let me share this over here. So can you guys see this IPython notebook, Tensor Contraction?
Yes.
Okay, good. So as this describes, in this notebook, we'll compare the time scaling of wave function simulation with Tensor Network Contraction simulation for a simple circuit consisting of a RY rotation and a CNOT pattern. By the way, I should mention that I did not produce notebooks for the XCB stuff, because that already, there's a blog post that Will and I wrote that's hyperlinked in the slides. So you should just go check that out. That's useful. That should serve as your exercise tutorial. And then at the very end, oh, I guess I forgot the last slide over here. At the very end, I have, I would suggest to you the following exercises. So, to start off with is the warm-up exercise. I would say recreate the Puerto distribution and also calculate separately XCB. So notice that those are two different exercises, right? And there are 4 versions of those exercises. One is to produce, use random unitaries and an ideal wave function simulator. And for that, you should basically go over this blog post, and it describes exactly how you can do something like that. The first variation you should put on that is, instead of using an ideal wave function simulator, you should use a simulated quantum computer. So this is where you will actually sample from, say, the QBM, which is something that we did last time. Then the next variation that you should do is replace random unitaries with random quantum circuits. And so for that, the idea is we describe how we could use this Rigetti gate set over here. So for your single qubit gates, you can use 1 Q. For 2 qubit gates, you can use something like that. And then you can use a qubit layout that looks something like this. So the boxes or the rectangles over here denote your 2 qubit structure layout, or your 2 qubit circuit pattern, right? And the idea is that you have a single layer of just random 1 qubit gates, followed by some 2 qubit circuit pattern that looks like this, and then followed by another single qubit layer, and then followed by a 2 qubit gate pattern that looks like this, followed by another single qubit layer, followed by a 2 qubit gate pattern like this. And so you will just have repeating patterns like those, and those are your random quantum circuits essentially. So you can do that, and then again just use an ideal wave function simulator. And here, so this thing, you could basically, when I say an ideal wave function simulator, you could basically just do it in NumPy. Over here, you can basically use Python's wave function simulator. And finally over here, again, you'll use the random quantum circuits and a simulated quantum computer. And I will send out the solutions to this, if not tonight, then in a few days. But you should definitely try doing this yourself, and then and only afterwards look at the solutions, I guess. But okay, let me go over the Tensor Network Contraction stuff. So here, the claim that I made, I'm just going to show you how it works in code. I'm going to explore that circuit that I described to you, the CNOT ladder from on between 2 and 23 qubits. So first I'm going to do wave function simulation. And so all this is doing is that, basically for some number of qubits, it initializes a QBM that's relevant for that many qubits and picks random angles, right? Applies an RY rotation about those random angles, and then basically just produces a CNOT ladder between them. And so it produces the wave function, and notice that I'm not really doing anything with that wave function, but if we really wanted to use the example that I gave you in the slides, you could do something wave function get probability of the all zeros bit string or something like that, right? But that's just a constant time function, and the real computational difficulty is coming from just computing this part, right? So I'm just timing this part, right? And I'm saving the time difference in as a dictionary, basically, as a dictionary item. And so here comes like the tensor network contraction style of doing things, right? So remember that we talked about um, the fact that like Ry is a rank 4, sorry, a rank 2 dimension 4 tensor, right? So dimension 4, and there's 2 of these indices, right? So this is, that's going to specify my Ry tensor. I'm just, for simplicity, I'm calling S and C to be sine and cosine theta over 2. Then basically, like, you can just work this out on paper and see that, like, okay, like it's 0, 0 component should be this, 0, 1. You can basically just work out all the components one by one. And that defines your Ry tensor, essentially, as a function of the rotation angle theta. So you have that, and your C naught is a dimension 4, rank 4 tensor, right? So dimension 4, and then there's 4 of these indices, so that's the rank 4. And now again, I mean, you can basically just go through the exercise. Oh, and I guess uh, this is a little bit of a simplification. What I really mean to say is that, strictly speaking, it should be, um, represented on IJ tensor KL, right? But like, I mean, but basically you'll notice that if you go through this list, a lot of those things just come out to be 0. And there's only a few handful of components that are actually equal to 1. And so that's why I'm basically, being a little bit sloppy with these comments. But essentially, there's only like 16 components that are equal to 1. You can check that, like, this list matches that one. And so I'm basically saying, like, okay, by default, set everything to 0. There's like 4 to the 4, which is, a huge number. And but only this 16 components are going to take on the value equal to 1. And that's my C naught tensor. And finally, like the 0, 0 state is the tensor 1, 0, 0, 0, right? And what I'm going to do to contract my tensor is use NumPy's einsum. So this is a very nice um, piece of NumPy that allows you to perform what's known as Einstein summation. Okay, it's just like Einstein summation just means that, like, if you have, like, Einstein used this convention, I guess, in when he was describing relativity, where if you have like repeated indices like I and I in some tensor, that implies that they're being summed over. Okay, so hence Einstein summation, or hence einsum. So you should go over this if you're not familiar with this. This is a very useful part of NumPy that can oftentimes speed up a lot of computations. Sometimes it doesn't, sometimes it does. But anyway, it like allows you in general to very controllably sum over arrays that have multiple indices. Okay, so like, I mean, if you had like some very complicated NumPy array of like very weird shape, and you wanted to, like, sum along one particular axis, then einsum sort of does that for you. So for example, like, this involves like 2 rank 2 tensors, A and B. A has indices, we're calling them I and J. And so this einsum ij comma jk ab basically says, like, okay, the second rank, or I guess, like, I mean, the second axis of A should be summed with the first axis of B. Okay, and you can of course imagine like much more complicated. Like, I mean, you can do you can take traces, and you can do like, you can basically get like trace over the first and the last axis and so forth. Um, you can do all sorts of crazy stuff with einsum. So anyway, I won't really go over all of that. There's some nice examples over here as well. But my point is that I'm basically using einsum over here. So as you can see, what I'm doing over here is, first of all, I am contracting the Ry's with the C naught. Okay, so if I go here, I'm basically saying, like, okay, C naughts, like, I mean, each Ry, just like to the left of a C naught, contract this thing with this thing, and likewise contract this thing with this thing. So that's what this thing is doing, right? Like, I mean, it has a left index, which is joined to the qubit, and there's a write index which is joined to the 2-qubit gate, and that is going to be contracted with one of the indices of the C0 gate. So I do that for each of the RY C0 pair. And then, the C0 then, after that, basically, let's see, I am then contracting like each of these qubits along, basically over here. Like I say, like, okay, like the starting state, like row 0, that's going to be like my qubit over here. And maybe, I guess I don't, can you guys see, like, if I click on one of these qubits, it gets highlighted? But anyway, I'm basically just saying, like, like each of these circles, for example, this has to get contracted with one of these rectangles. And that's basically my row 0, which is specified by just, a single edged tensor that gets contracted with this edge of the C0 tensor, and then row 0, which is the measurement node, right? That gets contracted with the C0 tensor as well. And so this K gets repeated with that K. So finally, now, like, I mean, those C0s, then I just collect together in a list, and those now are my, this linear array of C0s, right? And so now these I can simply just contract over as well. So this is like, I mean, just like, this is now a fairly simple contraction. And then I left over just one final row 0. This is just like sort of like a relic left over from the fact that not all of the row 0s, not all of the tensors, this through that, like, actually got contracted. One of them got left over. So that final one is like the only thing that I'm taking care of over here. But essentially, that's essentially the idea. And you can see that this, oops, RY, I guess I didn't define this, define that, define this. You can see that it works like blazingly fast, right? Like it went all the way up to 23 qubits. And so now if I plot this, you can see that kind of like, nice scaling. The tensor network contraction, like, because it never exceeds, because nothing, no matter how many qubits you have, no vertex ever exceeds, like a maximum degree of 4. This is essentially like almost like a constant time computation, right? Like, I mean, it's not exponential. It's not like, it's maybe linear, at best, but like, it's basically like a pretty, like, almost like a constant time computation. Well, okay, I shouldn't say constant time, but like, I mean, linear in the number of qubits. But like linear in the number of qubits compared to something that's exponential in the number of qubits, that's a huge, huge, huge gain, right? And that's why you can do this for something like, like you could replace like n qubits with 500 and still be able to get a value pretty quickly. So that's one example of how you could use tensor network contraction. I would invite you to try this for other more complicated circuits as well. You should all get this notebook and play around with it. Okay, so any questions about XCB or tensor network contraction or any of this stuff?
Are there alternate formulations that are equivalent to network contraction? Because we could say that, hey, rather than running the full wave function simulator, we are really interested in calculating just one of the amplitudes, and let's be just smart about doing that computation because we just keep progressing that computation over that specific amplitude. And so there's an alternate way which perhaps is still equivalent.
Equivalent to what exactly?
In terms of complexity to network contraction. So the way network contraction is doing the computation for a single amplitude, could we be smart about it in some other way and still end up with a similar analysis?
Good question. I'm not exactly aware of such a thing myself. Maybe it's doable. Are you talking like in the context of like wave function simulation exactly?
Well, wave function simulator for sure would not do it, right? Because there we are just kind of brute force saying, hey, let's compute the whole thing. And
Exactly. Yep. Yep.
for the specific example we've done for network contraction, we've kind of said that, hey, we're really interested in just this one specific amplitude, and here's a nice way to compute it specifically.
Yes.
Now, could I go back to the wave function computation model and say, hey, over there also, I don't really want to compute the entire vector all the time. I'm just really interested in this one specific amplitude. And given a circuit, here's a nice way to do the computation that allows me to, get that guaranteed, get the amplitude out correctly for that one specific entry.
So the only way that I'm aware of is using this kind of tensor network contraction method. Like if you're only interested in like a single amplitude. I should say that like there's a whole set of like other simulation methods which like broadly the idea with those are that like instead of so here what we're saying is like we're actually simulating the entire circuit in some sense, right? There's an alternative way to do it, which is like you say, like you use a classical computer to produce a probability distribution that mimics what the probability distribution produced by the quantum circuit would be. So, like, I mean, there could be like, you could say that like, okay, certain quantities in expectation would be the same if you sampled from this probability distribution, which I can generate on a classical computer, versus if you generated the true probability distribution on a quantum computer. So there's simulation styles like that, which are sort of like more probabilistic in nature. Here, you're sort of like computing the exact amplitude, right? And so when it comes to computing the exact amplitude, which is some number, yeah, I mean, the only one that I'm really aware of is this kind of tensor contraction style. Another thing I'll mention, by the way, is that like there's one thing I did not mention over here is using the kind of like the so-called Feynman summation technique. So Feynman, famously came up with this alternative way to describe quantum mechanics using the so-called path integral formulation, right? And in the path integral formulation, this is like a sum over histories interpretation of quantum mechanics, right? So the idea is that like, so in quantum mechanics, like we're often interested in like, here's some final state, which I'll call X final, and here's some initial state, which I'll call X initial. What is the overlap between these states, right? And X final is something that you get from applying some, say, unitary matrix between, or unitary operator between X initial to X final, right? And so Feynman said, well, okay, it's like actually like, in the path integral formalism, you can compute this as like a weighted sum of all paths between initial and the final state. And those paths are like, like, I mean, going from here, an electron, and going from here to there, not only travels in like, maybe say like the classical path, which is perhaps a straight line, but also this curve, and also like a curve that winds through San Francisco, and also a curve that's goes all the way and visits you guys in Pakistan, and then comes back over here to my desk and hits X final, and it goes through all possible paths. But each of those paths are then weighted by the action, by the classical action that governs that that particular path, right? So in the context of quantum computing, what that means is what people do is the following. So they say, yeah, so let's take like a gate like C naught, for example, right? Now, instead of say instead of actually computing or simulating like the 2-qubit gate C naught, what we can do is if we just look at this first term, 0, tensor I, this is like 2 single qubit gates. Well, not gates. I shouldn't use the word gates because 0 is a projector, right? It's not a unitary operation, but it is an operation. It's a projector operation on a qubit, right? So we can think of this as like 2 single qubit operations, right? In which on one qubit, like I applied the projector 0, and on the other qubit, I applied the projector I. And in this other term, like this is like, if I apply the projector 1 on qubit A and the operation or the gate X on qubit B. So what I can do is I can actually produce 2 simulations in which instead of applying a C0 gate, I will actually just think of like, if this was like, say, a 2-qubit simulation, I will actually instead do 2 single qubit simulations in which, like, I only have like single qubit gates, right? And then at the very end, I'm going to get some amplitudes, which I can then, assemble together and produce the final amplitude, which would have been the case if I had computed the entire, like this, done the actual C0 simulation. So the advantage that that gives me is that I don't actually have to simulate the entire set of qubits that I have. And instead, I can do, for example, like, if I have, like, say, a 16 qubit chip, and my laptop can only really feasibly do 8 qubit simulations, for example, right? Then I'm not going to simulate the entire 16 qubit chip. I'm going to say, like, okay, if there's C naughts between, like, say, 2 of the 8 qubit, sublattices, then I'm going to basically break apart those C naughts into these 2 Feynman paths, and then basically like simulate the 8 qubit chip separately, and then only at the very end I'm going to amass them together. So these cuts, like these so-called Feynman cuts, the trade-off is that, like, now you have like 2 raised to the power number of cuts. That's how many different paths you now have, and those you need to sum over. But each individual path becomes a bit more feasible, right? So that's another way of sort of like computing amplitudes, I would say, which isn't orthogonal to what we were discussing. It's just kind of like more complementary. And of course, like those sub simulations, they don't have to be tensor contractions necessarily. Like they could still be like brute force matrix multiplications or wave function simulations, or whatever you want essentially. Um, but yeah, I mean that's the idea.
Yeah.
Any other questions or thoughts or comments?
And then I guess one of the references that you referred to give the upper bound in terms of that we will still have some cases that are difficult for tensor contraction to do
Oh yeah,
efficiently.
yeah. Yes. I mean, notice that like this is going to be exponential in something, right? Like I'm being loose with what I defined, but like if this wasn't exponential, then like this wouldn't have been a quantum supremacy experiment, right?
Right.
So we the it's not exactly exponential in the number of qubits, um, but it can be, right? Like, I mean, so for if you're limiting yourself to 1D lattices, so if these qubits are all like on a lattice that is kind of like a straight line lattice, right? Then like if your number of qubits, for example, is smaller than the depth, for example, then this is exponential in the number of qubits. Um, it's just like that's just like a result that follows from, like, that's basically because the tree width is actually proportional to the minimum of either the depth or the number of qubits. But more exactly, this classical simulation cost using tensor network contraction scales exponentially in the so-called tree width of the graph. And that, like, I mean, I think, like basically it's like related to the maximum. We talked a little bit about why you should limit the maximum degree of a vertex during a contraction. So this maximum degree is like loosely, you could think of that as, kind of related to the tree width over here.
Is there a characterization of the kind of networks for which this will give an efficient bound?
Yeah, I mean, if the tree width is like really limited, like, so for example, for the C0 ladder, like there's not much of a tree width, right? So like the max degree, like we mentioned, like it never exceeds 4. So this is an example of something that's very efficiently simulated, right? So even though, like, I mean, there's, notice that like people love to throw things like, oh yeah, you like if you just have entanglement and you just have like coherence and you just have a lot of qubits, then no way can a classical computer ever reproduce that. But like, look, I mean, there's non-Clifford, like, I mean, operations over here because we have random RY things, right? There's C naught, there's entanglement, there's coherence, there's all of those things, but still, and we have a lot of qubits, but still, this is something that's very efficiently classically simulable. So just things like entanglement and coherence, those things don't guarantee alone that a quantum computer can have an advantage over classical computers. Like, I mean, it's a lot trickier than that.
But is there some work in terms of characterizing the cases for which, in general?
Well, yeah, I guess, so I guess the most general statement that I'm personally aware of, because I'm by no means an expert on this area of classical simulation, is that, like, if you can show that there's like a family of graphs whose contraction, whose free width is like limited, then, so that's, I guess, like the most generic statement. And this is one example, right? But I'm sure there's like whole families of examples like that.
Right.
But basically, like, the idea is, like, intuitively, like, I mean, you should just imagine that, like, if you have like a deep circuit and a very well-connected circuit, then those types of circuits are in general hard to simulate classically.
Thank you.
When you're saying that it's not going to more, is that only for this kind of data or this kind of depth for the tree, or would it exceed more when it's more complex or more layered?
I'm sorry, I didn't quite understand the. I
And
didn't I
then
didn't hear the question properly. No, not very better. Is there a microphone or something that we could?
we can.
Just loud. Try louder.
Now can you hear me?
Yes, much better.
Okay. So I wanted to ask that you said that max degree won't exceed 4. So was that for only that kind of C0 ladder, or would the tree depth affect that? Here you wrote like you said that max degree for the vertex during contraction process never exceeds 4.
Yes,
So
yes.
is that for more complex trees, or like with more depth? Or be different for those, or would that exceed 4 in that case? What does this mean here?
So
in
what this means here is that if you so let me go back at the presentation mode so I know that I have the pointer. So what this basically means is that I'm not limiting the so this might be a little confusing because I have like 4 of these nodes over here. That's not, sorry, bad example, because this could be like hundreds of circles over here and hundreds of circles over here. Okay. The number of circles or the number of qubits doesn't really matter. That's kind of like the main point. What matters is that I have like this structure of like single qubit gate followed by a 2 qubit gate that entangles this current qubit with the one below it. Okay, so the contraction ordering is as follows. First, I will contract this circle with this square. Okay, then I will contract. So now I only have like this edge is gone, right? This edge no longer exists and the circle no longer exists. The circle has been absorbed into the square. And then I will contract this square. So notice that that operation, the contraction of this circle with this square, is something that is exponential in like it scales as so let's say that the dimension was 4, which it is in the case of these quantum circuits, right? Then this is a computation that scales as 4 squared because I have 2 edges over here, right? So good. Okay, so like, I mean, that's something that like takes me 16 computations, and now I only have a square. And now this square I'm going to contract with this C0 gate, right? And so this thing is going to be something that scales as 4 to the 4, right? Because this thing, like, I mean, there's one edge over here. Remember, this edge no longer exists. There's one edge over here. There's one edge over here. There's one over here, and there's one over here. Remember that, like, the exponential cost, if I scroll back a few more slides, it was exponential in n plus m plus p, like, I mean, that's how many operations I needed to perform a single tensor contraction, right? So where p is the number of edges that are being contracted over, And in the case of the quantum circuit, like contraction, P is always just going to be 1, okay? Um, in the particular diagram that I was showing you just now. And A, A was one node and B was another node, right? And so like these have like separate legs in total of like n plus m. So the whole operation is exponential in n plus m plus p. So that's why, like if I go back over here, um, when I contract the circle with the square, that's like exponential in 2. When I contract the square with this, that's exponential in 1, 2, 3, 4, right? And so now I have like 3 of these edges remaining, right? But before I contract any of these, like I'm also going to contract this circle with that thing so that this edge now disappears. I'm going to contract this square with this rectangle so that basically this edge disappears. And now there's only a single edge between this rectangle and this rectangle. I'm also going to contract this thing so this circle with that rectangle, this circle with that rectangle, and then likewise there's another square over here and another like 2-cubic gate over here, and I'm going to contract this square with that rectangle, and then this circle with this rectangle, etc. So basically, I squish all the circles with these squares. And the squares with the rectangles, and so that gets rid oh god that rids itself of a lot of these edges first of all. And once I have gotten rid of all of those edges, where'd my other C naught, there we go. So once I've gotten rid of all those edges, basically I'm left with these rectangles or these C naught gates that only have like a single edge between them, right? So remember this square I contracted with this rectangle, right? So I got rid of this particular edge, and now I only have like a single edge that goes from this point to that point, right? And I got rid of this edge too because I contracted the circle with this, and I got rid of this edge because I contracted the circle with this, and any kind of single cubic gate that was coming over here, I got rid of that as well, et cetera, right? So in essence, basically, and all of those operations, like they never exceed, uh, those like never involve any vertex whose maximum degree exceeds 4, right? Because when I contract this with this, that involves a vertex whose, that only involves 2 edges. It's an exponential in 2 edges. When I contract this with this, that's exponential in 4 edges. But that's the maximum like computation scaling that will ever happen. It never exceeds 4. On the other hand, like I can basically continue that process uh, for a very large number of qubits. And as this sort of advertised, I specifically did it for like 500 qubits, as you can as well if you take that notebook and just replace n qubits with 500 instead of 23 or however much we went up to, you'll find the same thing. But the idea is that like you can if you just follow that contraction ordering, then you can sort of like this becomes a very quick way to simulate the amplitude. Now, there's a very dumb way of doing this as well, which is that like you end up you don't contract any of these circles, right? So you only contract the square with the rectangles first, right? And then once you have like circles and like this chain of rectangles in the middle, and then these circles. These circles, by the way, are the starting qubits. These circles at the end are the measurement scenarios. And these are now your 2-cubic gates fused with the 1-cubic gates, right? And then, the dumb way to do it would be like, okay, you say, I'm going to contract each of the 2-cubic gates with themselves first and build one very large rectangle in the middle. Well, that's going to produce a vertex that has like, 2n edges or 2n legs, right? And so that's a computation that's going to scale as it's going to be exponential into n, or exponential in n. And so you're back to kind of the exponential scaling, which is what you wanted to avoid. So the way, the order in which you contract these indices or these edges can make a huge difference between whether your computation is going to scale, linearly in this case, or exponentially if you did it, if you contracted this network in kind of like the naive way. Does that make sense? Does that
Yeah, it
answer your
does.
question? Okay, good.
Other questions?
So the complexity of some the complexity of some circuit like this, is it the exponent of a maximum degree of whatever we had, or is it just applicable on the C naught derivative?
Is it, sorry, I didn't get that last part. Is it exponential in what again?
The maximum degree of our circuit is the complexity of the entire simulation just the exponent of the maximum degree?
Yeah, essentially. Like, I mean, so, like whenever we say that like an algorithm has uh, scales as order or something, right? Like we're basically, we're usually saying like, I mean, like this is like the order of like the thing that scales the most, right? Like, so if you have something that scales as say n to the 4 in your computation, right? But you also have like 100 different computations in there that scale as n squared, then you say asymptotically, like in the very large n limit, like the n4 part is going to dominate, and you say like, okay, it's order n4. So complexity theoretic wise, like it's you could say that it's exponential in its order exponential the maximum degree, because that's the thing that really uh, like that would contribute the most in some sense. Now for specific exact computations, like where you really have to get down to like you have to pull up your sleeves and really do the work, then you have to sort of like start taking care of like, well, okay, exactly how many computations do you have to do, and what are the overhead costs if you do it this way or that way. But like, I mean, this sort of like analysis does sort of like help you identify which paths not to take for sure, right? Like if something scales exponentially and another thing scales polynomially, uh, doesn't matter what overhead costs or whatever kind of other tricks you do, you're going to lose badly if you try to do the thing that scales exponentially, right? Whereas, which in this example is very dramatic, right? Like uh, if we contracted everything in the middle first, that scales exponentially, and if we don't, then it doesn't. So that makes a huge difference in this case. Um, so that's kind of the point. But yes, I mean, like, like the point that like, uh, if we had done it in the middle, then even though it would be true that most computations might not involve, very large amounts of or vertices with very large number of edges, but like because we have at least one vertex that has like 2n edges, just that one single computation alone is going to kill you, and you will never get to anything like 500 qubits. Like you probably won't even be able to get past 50. Um, Probably a lot lesser than that on the laptop, right? So yeah, I mean, even if it's just a single computation, that can matter quite a lot.
So the contraction process depends on the ordering of the qubits rather than the number of the qubits.
Not the ordering of the qubits, the ordering in which you contract the edges. So remember, like, I mean, we constructed a tensor network out of our quantum circuit, right? So qubits, I mean, you could think of them as like starting out their life in these initial states, right? And then they sort of like proceed along these lines, right? And then some gate gets applied to them, and then they go along these lines, and then like a 2-qubit gate gets applied to them, and then this 2-qubit gate acts on these 2 qubits, and so this qubit carries on its life along this line, whereas this qubit carries its life along this line, right? So you initially have some quantum circuit out of which you create this network of tensors, right? But once you have this network of tensors, now you should just forget all about qubits and gates and everything, right? Now, the only thing that matters is that this is some graph. This is some undirected graph, and you have to contract this thing into a single number. And so the idea is that, like, like whenever you have a graph of tensors, like you have over here, uh, the order in which you contract the tensors matters. And so we're not talking about the order of qubits or anything at all, right? Like we're talking about, like, we have to contract edges. And so should I contract this edge first, or should I contract this edge first? And then, let's say I contract those edges. After that, should I contract this edge first, or should I contract this edge first, right? It doesn't really like make sense to call this like qubit A and this edge something else, right? Like, I mean, qubit A was living on this edge as well as this edge as well as this edge, right? And once you've actually, like, I mean, done all those edges, like sometimes like it becomes kind of like pointless to talk about which edge was, which qubit. Like maybe like at the outset, like these edges have some interpretation of like, okay, this qubit lives on this edge as well as this edge and that edge. But like once you've actually contracted big parts of this network, that sort of identification ceases to make any sense after a certain point. So I think the most useful way to think about this is that, like, initially it's, of course, you are working with qubits and everything, but you draw out a quantum circuit, and now you map it to some network of tensors, like we have done over here. And once you have that network of tensors, forget all about qubits and everything else. Like now you just have a graph of tensors. And so now your job is to contract this graph of tensors into a single number. And the best way to do that is to make sure that whatever order in which you contract your edges, make sure that you don't end up with a fat node or vertex that has too many legs, right? You want to avoid, you want to contract your graph in such a way that you, like, every vertex is thin and has like a small number of vertices or edges, essentially.
So just one final bit from my end. I think I'm harping about the same thing again and again, but off the top of your head, if you were to try to do network contraction on a QFT circuit, do you know what comes out in terms of?
I haven't tried that, but a QFT circuit, like, I mean, it looks something like, you have these Hadamards, and then you have, like, I mean, controlled rotations, right? Or sorry, so you have Hadamards, you have controlled rotations about some angle that, like, basically gives you basically, like, I mean, the position of the binary digit,
Right.
Right? And yeah, that's a good question. I haven't tried that, but my guess would be yeah, it's going to involve, like, I mean, like, I mean, so basically, like, you no longer have a structure like this, right? Like, I mean, you have like a vertex that, like, involves, like, initially, like, I guess these two qubits, but then you also have, like, a vertex that involves this edge and this edge, right? Because now you have like a controlled rotation from here to there. Then you have a controlled rotation, from there to there, and a controlled rotation from there to there. So if you start contracting that, I would bet that you very quickly, get something that's going to. My guess is that you probably won't be able to avoid a vertex that has something like an edges, or something of the order of n edges. That's my guess. Because if it wasn't, it would probably be a very widely known, well-known result, right? Like, I mean, somebody, like, contracted the QFT circuit in, like, say, linear qubit time, like that would kill off a lot of potential quantum advantages.
Well, does it really? Because we are still going to be arguing that hey, using this process, I can compute one of the amplitudes, but there are exponentially many amplitudes to calculate. So, does it?
Sure, but you know, like that's a very good point. However, if you didn't really require, if you weren't exactly required to compute exponentially many amplitudes, but only say like n of them, right? Then like I mean, you know, like if you have like n times, you know, something linear in the number of qubits, that's a huge deal, I would imagine. Um, and I'm sure like people make use of stuff like that all the time. But yeah, I mean, like that's, well, again, I mean, you know, I shouldn't say concretely. Something to explore. I don't know if that's actually been explored. That's a great question. I don't exactly know. But yeah, I mean, it's, but I mean, that's my guess, is that like it probably won't, you know, like scale anything less than exponentially in some sense. But I mean, okay, so at the very least, we know that like, you know, it scales exponentially in the tree width, right? The question, I guess, then is like, okay, well, what's the tree width of that graph? And yeah, I mean, so that's the interesting question. Yeah.
Right, I think that's all the questions we had.
Okay. Okay. Let me also, I wanted to go over something that I, you know, because of some technical difficulties last time, I wasn't able to go over this, but I'll go over it now. This is the gate error mitigation, the digital zero noise extrapolation technique using Pike-Will. And what I'll do is I'll also pull up my slides.
May I recommend, perhaps it's good for you as well, we take a 5-minute break because I see the students just walking out of the room as well.
Yeah, that sounds great. That sounds great. I'll come back in a minute. Yep.
Thank you. So we take a break.
Values, and n is the number of CNOTs that you have in your gate. So we can see that basically this has the behavior of like, you know, y being like c times p to the n, where c I'm basically saying is the ideal expectation value, right? And so if we just take logs of both sides, we'll see that this is like the expression of a straight line, right? Like, so if I have log y on the y-axis and n on the x-axis, then log p should be the slope, and log c should be the y-intercept. And so from gathering data like that and then fitting a straight line to you know, like this transformed space, I should be able to infer what the depolarizing parameter p is and what the ideal expectation value c is as well. And so I've left that part as an exercise, but to get you guys you know, started, I set up this notebook where you will explore the idea of, you know, using the so-called digital zero noise extrapolation using Pike-Will. So, you know, we'll this is just basically defining some helper functions. This is actually something that's relevant to what we were talking about today. This is a method to you know, produce a Haar random unitary matrix over n qubits, essentially. So it's it gives you a matrix of dimensionality 2 to the n by 2 to the n. Okay. And this basically generates all 4 to the n possible Pauli operators over n qubits. So you have like the identity x, y, and z. This is basically saying like, you know, so that's the 4 possible Pauli operators on a single qubit. If you had a 2-qubit space, then, you know, it would be identity times the identity, identity times x, identity times y, identity times z, and then x times I, x times x, x times y, et cetera, et cetera. Right? So there's like 4 squared, 16 possibilities. And then if you had 3 qubits, then it would be 4 cubed, et cetera. So this just generates like all those 4 to the n possible Pauli operators and assembles them together into a list, you know, that I call ops list over here, and that just returns that. all of this extra junk over here is basically just doing a sanity check to make sure, and basically it sort of like helps you understand what it does as well. But basically what it does is that like if you have any initial arbitrary state, and I'm just like picking some initial random state. This is not necessarily a random, a uniformly random state, but it is nevertheless some reasonably random state, right? So it's a ket that I pick, like of size 2 to the n, right? That's the dimension. Each of them, numbers between 0 and 1, and then basically like I'll just normalize it so that it's so that probability is sum to 1, right? I'll construct its density matrix, right? This is like the ket, like the ket times its bra, right? So that's that. In NumPy, you can calculate it as the outer product of the ket with itself. And then basically, I'm just going to apply. Remember that the way that unitary operations act, or basically any Krauss operator in general, acts on a density matrix is it basically sandwiches it from the left and right. So like U times the row, U times the density matrix times U dagger. And the U dagger is just given by like, the operator represented by the array dot conjugate dot transpose. That's what a dagger means, right? And so basically that's, it's just making sure that this row prime, you'll realize if you do this exercise that basically like, if you sandwich, all the Pauli operators basically to this, to any initial arbitrary state, that thing basically gets sent to the maximally mixed state, which is basically the identity over the dimension. And this is basically some normalization factor. Okay. So this then gives you the list of all Pauli operators, which is important in generating the cross operators for the depolarizing channel. So the cross operators, remember, they have to satisfy this particular requirements, right? So they, along with the Pauli operators, they also have to come with certain probabilities. And so, the way you build it is you say, okay, first of all, I have like 1 minus probability times the identity. And then, I'm going to add like the remaining cross operators. And notice that like this is actually going to have 2 factors of the identity. One is coming from this thing, and another is coming from the fact that like, you have like a product of like all i's sitting in here as well. But if you work out the math, what it comes out to be is that like, this probability is going to have the interpretation of being the probability that you get the totally of obtaining the maximally mixed state, and 1 minus the probability is going to be, so if I look back over here, then I guess if I, right, so I guess the probability that I'm talking about over there is like actually this factor over here. So and the remaining probability, this is like, what I'm calling prob over there is like actually 1 minus p over here, right? So just shift your perspective of p and prob. But basically that's the idea, is that like there's one parameter, that's the coefficient of the totally mixed state, which is this thing, and then 1 minus that parameter is the coefficient of your original state. That's going to be 1 minus prob. And that's what we typically think of as gate fidelity as well, if it's like, some 2-period gate or something. So the exercise is basically like, prepare a Bell state, and compute the expectation value of the observable ZZ in this state. And you can compute just by hand that like, ZZ, it has like, like the only non-zero contributions are going to come from these like cross products between 0 and 0 and 1 and 1, both of which are equal to 1. And these cross products like between 0, 0 and 1, 1, both of those equal 0, right? So basically you'll have like, you'll have something like 1 plus 1 divided by 2, and you'll find basically like, the expectation value of the Z in this Bell state is just equal to 1, right? And so that's what we should find over here. I'll let this run and I'll say a few words. Oh, no, I guess it ran pretty quickly. But basically what I'm doing over here is like I'm initializing my 2-qubit QVM. I'm going to take 10,000 shots. And basically, this is just writing a Bell circuit program. Declare, initialize a program, declare its readout register to hold 2 classical bits. And basically, I'm putting in these pragma preserve statements. Essentially, the idea is like if you start off with like a pragma preserve block header and put an end at the very end, if you have a pragma end preserve block, everything between that never gets compiled away, so to speak, right? So it will remain intact. Like if you do qc.run or if you do anything else, like these instructions are not going to go away. And that's useful for our purposes because, remember that we're actually going to somewhat artificially introduce a bunch of C naughts, a bunch of extra C naughts, right? And so there's a danger that the compiler could think like, oh, maybe the user just did this by mistake. Like, 3 C naughts is really the same as a single C naught. So I'm just going to be smart about it. And even though the user specified 3 C naughts in a row, I'm just going to really apply a single C naught. We don't want to do that, right? In this case, like we actually want the 3 C naughts and we actually want the 5 C naughts, etc. So even though here it's just a single C naught, but I'm just introducing this general scheme over here so that you guys get used to it. And instead of a single C naught, you can like sort of like introduce more. But right now, there's nothing noisy about this, right? Like this is just your regular C naught. This is just your regular Bell state preparation program. And now you just measure out your qubits. Rapid num shots loop just specifies that like, you're going to repeat this for a certain number of shots. You don't have to compile it. You can just like run it in your program because this is the QVM, and you don't have to do the extra compilation step over here at all. As we discussed last time, like these results are going to give you some bits, like right, so zeros and ones, and in order to convert the zeros and ones to the eigenvalues of the ZZ observable, you're going to convert these into like 0 to a 1 and 1 to a -1, so you can do something like this. And then finally, to compute the observable Z times Z, you're going to take like Z on the first qubit multiplied by Z on the second qubit, and then that's going to be an array. That's going to be an array equaling 10,000 in length. And then you take the mean of that, and that's the expectation value of the observable ZZ. And that should come out to be 1.0. So now next, we're going to add some depolarizing noise. And one way to do this, my favorite way to do this, some people don't like it, but I find it to be safer than most other things. It's a bit convoluted, but I'll show you how it works. So the way I do it is we first define a dummy gate, just like some gate that we don't otherwise need to use for anything. And then we'll overwrite that gate with the depolarizing channel. Okay, so, and then basically we'll just like have this rule for ourselves where we'll say that we'll follow every use of a C naught with this noisy gate. So that in effect, what is happening is that our C naughts become a 2-qubit depolarizing channel. Not exactly the depolarizing channel described over here, because like over here, like you're sort of like, with some probability, you're applying the identity operation so that you get this the original state. And with remaining probability, you're applying like the all polys operation so that you get the totally mixed state, right? Whereas over here, like, I mean, the idea would be instead of the identity operation, you would apply a C naught gate with some probability. And with remaining probability, you apply whatever operation gives you the totally mixed state, right? So that's basically the structure over here. So I'll specify my gate fidelity. Again, initialize my QVM, I specify a number of shots, specify gate fidelity, and the probability, which is like the depolarizing probability, is 1 minus that value. Declare a readout register. I am now going to define some dummy gate, and this is where my random unitary helper function helps. Like I'm just going to generate some hard random unitary. I don't actually have to generate a hard random unitary, but the chances of like a hard random unitary being the same as like any one of the gates that I use in my circuit, those are pretty slim. Non-zero but slim, right? That's why I like to use a random unitary over here. So first of all, I'll define that gate, and then I'll basically overwrite that gate using define noisy gate. and I'll say like, okay, like, like basically that dummy gate operating on 0 and 1, replace that with the noise channel specified by these cross operators. So remember that a noisy channel is completely specified, by the effects that its cross operator basically have on the density, on any density matrix, right? So if I specify the cross operators, I've specified what the noisy channel is. Um, so I'm basically going to override that unitary matrix with some set of cross operators. That's what this step does. And now I'm going to, again, like basically sandwich all of everything in a pragma preserve block. And I'm going to apply a C0, but then I'm going to immediately follow that by this dummy gate um, acting on 0 and 1. And so this thing acts now as a depolarizing channel, right? But then everything else stays the same, right? Like, I mean, once I've done that, then I'm going to uh, measure out the qubits, wrap them in num shots, run the results, transform binary digits into Z eigenvalues, and then compute the expectation value of the observable ZZ. And what happened? Okay, I guess I did not define this thing. Let's try this again. Okay, and so this number now should come out to be approximately 0.8, which it does, right? And why should it come out to be 0.8? Because as we argued over here, in the presence of the depolarizing channel, like that overall expectation value, which we saw in the ideal cases is equal to 1, that gets scaled by an overall factor equal to this number p, which like this p now has the like the interpretation of the gate fidelity over here, right? Which is exactly what we specified the gate fidelity to be, 0.8. So 0.8 times 1, that's what this number should come out to be. And in order to exaggerate the noise in the system, remember, in order to extrapolate to the zero noise limit, we first have to exaggerate the noise, right? So in order to exaggerate the noise in the system, we can likewise apply 3 noisy C naughts. And the way to do that is, I'm just specifying like this variable, which will specify how many noisy C naughts I want, right? And so gate fidelity still stays the same. This never changes, right? This is just like the setup of my problem, I guess. And I guess this part never changes either, because this is always, but what does change is that, and again, of course, I have to sandwich everything in this pragma preserves. This becomes important now. It wasn't really important before, but it becomes especially important now because I am applying a bunch of C naughts, right? And the compiler can be fooled into thinking that like I did not really deliberately mean this. This was a mistake on my part, and so any extra C naughts, like I'm just going to replace them with the identity operation. But I don't want that, and that's why I need these pragma preserves. So basically, just like if I want 3 C naughts, if I want 3 noisy C naughts, then 3 times I'm going to apply C naught followed by this dummy gate. That's all that's happening over here. And then everything else is the same. I measure, I wrap, I run the results, convert to Z eigenvalues, and then compute the average of ZZ. And this thing should now come out to be something, like, I mean, because as we argued earlier, like, I mean, these probabilities, the gate fidelities, they actually exponentiate, right? So if I apply this 3 times, then I should expect that this expectation value should now be something like p cubed times the ideal expectation value, right? So p cubed, p is the gate fidelity, which is 0.8, and 0.8 raised to the power 3 is something like 0.512. So, not exactly close, but it's close enough to that. So the exercise that you all should do is to use this visual zero noise extrapolation technique as described in the lecture to compute the ideal expectation value as well as the depolarizing noise in the system. So I have a solution notebook for this, but I'll send it out to, I guess I have sent it out to Gibran, but you all should try and do this for yourselves first, and maybe if you get stuck, take a look at that. But like going back, it hopefully should be a fun and somewhat challenging, but also somewhat straightforward exercise. The idea is that like you would repeat this instead of like, over here and noisy is 3, but you would repeat like, instead of 3, you would also do it for 5, and you would also do it for 7 and 9 and 11 and 13 and many odd numbers. And each time you do that, like you compute like ZZ, you would just keep track of what that ZZ value is. You would like collect that into a list, right? And then basically like, you have a list of ZZs, those are your Ys, and you have a list of and noisy, those are your N's over here, right? Now you take the log of those ZZs and you fit that as a straight line versus the number of noisy C naughts that you applied, right? So this is like your y-axis, and this is like your x-axis, and then your model of best fit. And there's various ways you could do that. One way I like to do that is there's this handy part of SciPy Optimize called curve fit. Which basically like the API is very simple. Like, I mean, you have a function that will like apply some kind of like any fit that you want, right? Like, I mean, so you could do a linear fit, which is like mx plus c or something. I'm just cooking up like the names m and x and c, but you can call it whatever you want. It just has to be straight line format. The x data is like your the number of noisy c naughts. The y data is the number of the log of the ZZ values that you found, and everything else you can just ignore. Those are optional inputs. But then if you do the curve fit, then it's going to return these optimal values of the parameters that you use in your callable function, which in this case should be a function for a linear fit. And then it also gives you like the covariance of these optimal parameters, which you can fairly ignore. But once you get those, then basically like your slope will be log of p, and so you can take the exponential of that to get the probability or the gate fidelity. And then you can also take the exponential of the y-intercept to get the ideal expectation value. And so you should be able to show that if you do all of that, that the dipole or that the gate fidelity that you get, and or likewise the depolarizing noise, which is defined as 1 minus the gate fidelity, would be like respectively 0.8 and 0.2. And the ideal expectation value, which we showed earlier, would be 1.0. So of course it's not going to be exactly 1.0, but it should come out to be something pretty close to 1.0. So I'll leave that as an exercise. But if you get stuck or anything, like there's also a solution manual to go with it. And yeah, that's about all I had. Are there questions I can answer or things you guys wanted to discuss or anything like that?
More specifically, if there are any of the topics that Suhaib mentioned that relate to possible project topics that you're interested in, now would be a good time to ask. No?
I'm also, by the way, I'm happy to keep in touch. My email is sohaib@rigetti.com. These days I'm pretty packed with stuff to do, so no promises on immediate responses, but feel free to reach out. Like it's been fun doing this lecture series. I hope they've been useful to you. I hope they've been equally fun as well. But yeah, I mean, if no questions come to mind right now, then I'll give you all like the extra time. And yeah, I mean, I guess it's up to you, Gibran, how you want to proceed.
Actually, thank you very much. Again, I really enjoyed them, and I think we got to learn stuff that we otherwise probably would not have been able to cover in our class. I was also wondering maybe we could do a quick screenshot of all the attendees in class and the couple online as well. So let's, I think we might want to go to gallery view.